Hello again, folks, in 114. Think about it for a moment, I'm sorry. As promised, I'm going to go over the solutions to test number 2. Reason being, of course, today is Wednesday, March 31st, last day of the month. My mother's birthday was actually the day before. Anyhow, the material from test number 2 should be from chapter 7 through 8. These are the sections that we covered. The material, the PDF that you should be able to access, I didn't check it out, I'll do that in a moment, but I'm pretty sure it should be visible right now as of midnight. This is the test number 2, and it is comprised of 20 or so problems, 22 I believe. I put the formulas where I thought they would be important. Some of the questions I took from my lab, because I figured, well, there was a couple of them that I felt they really warranted explanation. All right. So we'll go through this. Yeah, it's 22 questions. It's been, I forgot. Okay. Anyhow, if you're following along, do print this out, and I'll go through each one now. Let's see. I'll put that aside. And maybe it would be good to turn my projector on here. Let's see if I have to adjust the lights. Glasses. Okay. That was weird. Alright. Good. Yeah, it looks like it's available. My sister's yucking it up next door. Heckle, heckle, heckle. Okay. Let's see, it's way too dark. Alright. But the camera looks like it's in the right place, so let me just hide this and expand this. Come on. That looks pretty good. Yeah, I'm gonna have to move the camera. Ever so slightly that way. Is that basically visible? I think my whole card, actually, I have to move over. There we go. It's always crooked ever so slightly, I hate that, but... Alright, that will suffice. Move the camera back now. Alright. Let's leave that. Alright, where's my eyes here? Alright, the reason that I left these, they're supposed to look like number lines here for for question 1 and 2, is I figured that if you're going to convert between units, if you're not comfortable with it yet, build a little table, a little diagram. Remember that the base units are, in the case of liters, it's liters itself. I was taught to always capitalize the letter L. Your textbook doesn't do that, it uses a script L. Alright. I'm not aware of any consensus on what the letter should be, other than what I was taught a long time ago, so I'm going to stick with what I know. In chemistry class, I'm quite certain they would do it that way. Anyhow, immediately to the right, I'm going to use the abbreviations, would be deciliters, and then centiliters, and then milliliters is all the way over here. You could, if you want to, just stick with that because the units that are involved are already accounted for. All right. On the flip side, though, if you're curious, this would be decaliters, all right, hectoliters, and kiloliters. Now, truth be told, even though these unit increments exist, they don't get all used, all right? But in order to successfully, not too often anyhow, in order to successfully translate from one to another, all right, it would be good to recognize what the abbreviations are and to label appropriately, right? You'd have to know that from here to here is so many spaces, and from here to here is so many spaces, and so forth, all right? Now, having created this little table here, all right, this is the unit milliliter that you would be starting with. So I'm going to put a little dot here, all right? And this is regular liters that you would be converting to. So if you drew a number line sort of like this, a horizontal line with increments like so, it would actually help you decide where the decimal point goes. That is the advantage to writing it more or less horizontally like this. How many spaces? 1, 2, 3 spaces. X marks the spot, right? So you're going to make 3 jumps with your decimal point in this direction. I would make little waves then. 1, 2, 3. And just to distinguish the decimal from where it was and now where it is, I would exaggerate this one. And then fill in the voids. Here's a 0, here's a 0. Right? If I wrote it nice and wrote it a little bit neater, it would be this: 0.00955 liters. If you want to get fancy, sometimes they put a 0 up in the front, but that's more for the your aesthetic sensibility, I would say. I was told when I was taught this years ago that, well, that makes it easier to find the decimal point. I'm like, I don't know, that's kind of debatable, really. It should be 2 zeros after the point. So this would be your answer. Okay. Similarly, if you're building a little diagram to answer this question, all right, identify what the base unit would be, grams in this case. That would be dead center on this diagram. All right. And immediately to the right of it would be decagrams, and then centigrams, and then milligrams, like a vitamin. And immediately to the left of it would be decagrams, as opposed to decigrams, hectograms, and kilograms in theory, right? Now, where are the two that are relevant? They're on each side of the base unit. But this is what's given to you, kilograms, and this is where you're going. So I'm going to put a dot here, kilo, and I'm going to count so many steps over to dg, which is, again, decigrams. So 1, 2, 3, 4. X marks the spot. All right, 4 jumps. In a number like 117, it's a whole number to start with. So where would you assume the decimal point is to begin with? You should always assume that it is immediately after the ones place. All right. Again, I'm using a decimal point because that's what we have in the United States. We don't use commas, at least for this purpose. All right. And again, if you drew a diagram, took the time, this would indicate which direction you move your decimal point. So make 4 waves. 1, 2, 3, 4, and I'm going to exaggerate that on purpose, and then fill in the void. 0, 0, 0, 0. In the US, we put a comma every 3. So on this side of the decimal, the left side. So this is what you would end up with. To write it a little bit nicer, a little bit neater, it would be 1,170,000 decigrams, right? That's the answer, right? Again, these units exist, all right, decigrams. They don't get used too often, they're not practical. Kilograms get used a lot, milligrams get used a lot. And standard grams, of course. Any box of cereal, right, or some food, right, is usually telling you how many grams of sugar and what have you. All right. All right, now the next one is for length, area, and volume. How many times larger is a square kilometer than a hectare? I threw this in because there's often more than one word to describe the same thing. Hectare is a good example of that. Right. A hectare is a square hectometer. All right, so You don't have to do this, but here's a diagram if we're talking about meters, essentially, is the base unit. Decameters, hectometers would be here, and kilometers would be here. I swear that's an H. Okay. They're only one increment apart. Right. Here's a slightly magnified view. Kilometers, hectometers. Okay. They're both larger in terms of their size compared to the base unit meter. Right. What I do whenever I get a question like this, which when it mentions square anything, a square kilometer, you could be very literal. Square refers to something with a degree of 2. So if it was kilometers, it would be km with an exponent of 2. And it's literally an area. Right? A hectare is an alternative phrase for hectometer, and since it happens to be a square hectometer, you would use HM exponent of 2, and this is still referring to an area, of course, for that reason, because it's an exponent of 2. Right. Essentially, let us figure out what 1 square kilometer is compared to a square hectometer, or hectometer, whichever you like. When I do this, I draw, to start with, an actual literal square. And think about it in terms of area. If we wanted to calculate the area of a square, we would need to know the dimensions in 2 orientations. So we would have a dimension here and a dimension here to worry about. If it is truly 1 square kilometer, and it just says A as in 1, then this would be 1 km this way, and this would be 1 km this way. Now, individually, right, how many kilometers is a hectometer, or vice versa? And now notice this is degree 1 and this is degree 1, right? It's only when you multiply them that you get this arrangement, and that's really what we're trying to answer. Right? How many hectometers make up 1 kilometer? If they are 1 increment apart, then this is the relationship. It would take 10 hectometers to make 1 kilometer. Same thing this dimension, whether you want to call it length or width. Right? 10 hectometers makes 1 kilometer. So if we were calculating an area, the area would be 1 times 1 in terms of kilometers, right? But each one of those is 10 times 10. So what is 10 times 10 instead of 1 times 1? Since we're using hectometers this way. It would be 100. 1 square kilometer is in fact 100 square hectometers. Right? So to answer the question, how many times larger is it? It's 100 times larger. Right. Get in the habit of breaking something down into a literal drawing. All right. If they're talking about a square, draw an actual square. Right? It doesn't have to be beautiful, but to get the point across that it is this dimension and this dimension are the same. All right, whatever the unit is. Okay. Now, when you get to something like this, we're going to build on that idea, but we're going to have to make one little adjustment, because notice what is written here. The relationship that they're asking about to convert in this problem is 10 cubic meters versus so many cubic centimeters. If you'd like, draw another picture, and I think I will. Just to free up the space, I'll do that over here. And maybe adjust my camera a little bit here. On a diagram describing meters and centimeters, the base unit would be meters, then immediately adjacent to it would be decimeters, and then centimeters, and then technically millimeters, right? Okay, now, we're talking about a volume in this case. It's implied. How come? Because there's an increment of an exponent of 3 in each case. Right? So draw a cube because of the exponent of 3. It's really a volume. So here is a cube. That's a square face, and then one slightly offset behind it, and then connect the corners. And there you have it, right? Now, if it is a cube by definition, what is true about a cube? All of the edges are the same length. So this would be, using the original unit, a meter. So 1 meter, and then the increment this way would also be 1 meter, and then the increment this way would also be 1 meter. All right. I know that this says 10, but let's just stick with the basic relationship first. All right. So if we had 1 cubic meter, let's figure out how many cubic centimeters is that first. Okay. What is the relationship between meters and centimeters? Right. It would be basically 2 steps this way, right, to convert from one to the other, which in terms of a decimal would mean make 2 leaps with the decimal point, and therefore it would be 100. Not cubic though. 1 first degree. 1 centimeter is 100. Pardon me. 1 meter. I'm a little stupid right now. 1 standard meter is equal to, based upon this translation here, 100 centimeters. You might know that intuitively anyway, but let's say you didn't. Right? It's 1 to 100, which means that this measurement this way, along the arguably the length, would be 100 centimeters, and therefore this one would be 100 centimeters as well, and as with this one. So if we have this to start with, and we could conclude that from just the basic relationship of diagrams, a horizontal number line, if you will. Let's figure out what it would be if I calculated the actual volume now. A volume, instead of an area, would be an extra dimension multiplied. So instead of it being 1 times 1 times 1, it would be 100 times 100 times 100. Okay? You could use a calculator, but there's some way around it too. If it's just 1 times 1 times 1, that's 1 in the front. How many zeros are there total? 6, right? So that's 6 zeros after it. And that means that the relationship of 1 cubic meter is actually 1 million cubic centimeters. Right. Now, you might be satisfied and go, all right, well, mission accomplished, right? But just remember, one thing that we have to do now is take into consideration, this is not 1, this is in fact 10. So if the relationship is now 1 to 1,000,000, all we would have to do really is multiply by 10, right? If in theory we would be multiplying by 10 here, then multiply this by 10 here, right? And that's just going to add a 0, right? What you will end up with is this relationship, right? 1,000,000 times an extra 10, all right, would be 10 million cubic centimeters, and that would be your answer. Right? Start with the basic conversion factor. Right? It's 1 meter. All right, is 100 centimeters. Then calculate the volume, which would require you to multiply 1 times 1 times 1, or in the unit that we're interested in, centimeters, it would be 100 times 100 times 100. And then if they're choosing some other number here, like 7 or whatever it is, you just multiply by that number as an afterthought. right? Hence it's 10 million. 10 cubic meters is 10 million cubic centimeters. Okay. Next one is an area question. Hopefully there's enough space here. Find the area of the shaded blue region. This is the sidewalk basically around the house, right? An aerial view. This is Schmutz from the last problem. Okay. There's probably a couple of different ways you can do this. This is the way that it occurred to me. I don't want to dissuade you from doing something you do intuitively. But look at it as being, there is a very large rectangle. And then there is a smaller rectangle on top of it. And if we're trying to figure out basically just the blue walkway that goes all the way around it, apparently uniformly, all right, we're trying to figure out what the area of this sort of square donut would be. So let's call that the area of the square rectangular donut. Right. What would it have to be? Right. Think of this as an artist would. Right. If you're using some kind of software like it's the one I used to use. It's been so long. Oh, for crying out loud, I can't remember it. Something Scape. I used to use a software. I don't have it anymore, I'm so sad. Forget it. I don't know why I'm struggling to remember the name of the program I used to use. It was called something Scape. Anyhow, you would take advantage of basically this idea of having your software draw a particular shape. And then if, again, you want something that's not normal or rectangular donut, you would subtract out a similar shape, embedding it on top, you know, or from the top. Anyhow, so you might think of this, not babbling, as the blue area that is a rectangular donut, for lack of a less verbose way of speaking, would be equal to the area entirely minus, because it's just going to be the donut shape, right, the orangey, I'm just highlighting in red now, the red area that is a rectangle. And that's probably a little bit too much information, but better to be very thorough, I think. Better to over-explain than to under-explain. I'm essentially going to subtract these two things. Now, as for the dimensions, all right, we can glean them from the drawing here. Inkscape, that was the name of the program, Inkscape. This was free software, right, in lieu of using something like Photoshop. Anyhow, in Inkscape, a lot of times you would end up doing this. You would basically, if you're trying to create some three-dimensional figure, you would start with a flat, two-dimensional figure, and then if you wanted to have a hole in it, you would basically superimpose one shape upon the other, right? And then tell the software to basically cut it, right, in that arrangement, and there'd be a hole then. Anyhow, I'm over-explaining too much in a different direction. The formula for a rectangle is what? It's length times width. So we would need to know the dimensions of this entire rectangle, all right? And that's a little obscure, right? Because some of the information it's all there, but it's not given to us down at the edge here, right? It's in the middle, more or less. The distance from the edge here to the beginning of this orange or red rectangle is 1.4, right? So it's 1.4 meters plus something, right? The distance across up to this other edge here is 23. So 23 meters, and then it is another 1.4 because the walkway is uniform all the way around. So another plus 1.4 meters. Add these together, all right, what would you get? Well, 1.4 times 2 is 8, 2.8. So if you added these, you get 0.8, and that's 5. It should be 25.8 meters from here to there. All right, unless I'm crazy. No, that's correct. Good. So, all right, I'm going to fill that in now. 25.8. All right. We will have to do something similar with the width dimension. All right. In this instance, again, they didn't write it along the side as they often would. We know that it's 8 meters from here to here, just that far. But if it's a uniform walkway, it would be 1.4 there, and it would also be 1.4 there. So 8 plus 1.4 plus 1.4, all right? That's 2.8, all right? 10.8 is what you will use as a dimension. Okay, that would be the width in this case, 10.8. All right, and I'm going to hold off now. The second rectangle here is a lot easier. All right, it's still going to be the same formula for a rectangle's area, which is length times width, right? But it's explicitly stated. It's 8 meters this way, and it's 23 meters this way. So no guessing. All right, 23 by 8. All right. Now the reason that I put these parentheses in, I included them, is because we have several operations in theory that are going on here. All right. We have multiplication from the two areas that we would have to calculate, and then we have subtraction. I put the parentheses here because we really should calculate the area independently of each other first. So make sure that you do that. You can just enter this into your calculator exactly as you see it. 25.8 times 10.8. Close the parentheses, minus, open up a second one, 23 times 8. And then it will spit out the answer with your machine. But do be careful. You would have to remember to incorporate these parentheses because the calculator may not understand the order is in a certain specific order. Okay? So what should you get? The area that we're looking for, right, should be equal to, I want to say 94.64, and the unit is consistently meters all the way around, meters squared. All right, let me just verify with my own calculator here. And I'll hold this open. Okay, clear. 25.8 times 10.8 minus 23 times 8. All right. Here's as I have typed it, or entered it. You see on the screen, sorry about the glare. I've incorporated parentheses. This is the first encapsulation here is the first area. And then the second one is the red one. All right. Now if all goes according to plan, there you have it, 94.64. Okay, cool. Sometimes the hardest part is just setting something up. All right, for the next two, converting from Fahrenheit to Celsius and vice versa, I incorporated the formula, included it, so you don't have to go fishing. It would be good in the long run to memorize a lot of things. Factual information, basic facts are always good to assimilate. You know, and you should, when you're in the position of teacher, do encourage that. You know, have your students memorize some fun facts. That sounds so silly, right? But it's true. Like how to convert from Celsius to Fahrenheit. It will be practical in the long run. All right, but when you give them a test, be a good sport, and give them that. Even after you tell them to memorize something, give them this. All right, they will be so grateful. All right, and then the anxiety will just probably make them remember it from there on out. It's not to be manipulative, but you want people to do the right thing, right? It's unfortunate that when you take a test, a lot of times it's the anxiety, the experience that either makes you shut down completely and you go into panic mode and you don't do anything, you blank, or it has the opposite effect that you remember something because of the weirdness, the uniqueness of the experience. Sadly, for not the best reason, because you were worried, but anyhow, tell them to memorize stuff and then give it to them anyway, is what I'm getting at. All right, so here you have 89 degrees Fahrenheit. We'll see what that translates to in terms of Celsius. You have to follow the order of operations again, so your fixation should be on this inside of parentheses. Insert the value that is given to you, 89 degrees, and then follow the order of operations. If this is encapsulated as so, you really have to subtract before you apply the multiplication of this fraction. I'm going to get rid of that cursor. Okay. So if you subtract 32 from 89, you get 57. You may end up with a crummy sort of fraction, but it's a 9, don't be. But you can handle it. If the difference between 89 and 32 is 57, then if you're multiplying it by a fraction, just stick a 1 under it. If it were possible to simplify first, I would. You can't in this situation, you're kind of stuck with it, unfortunately. So you see what you get, all right? Top times top, bottom times bottom. This is going to be something over 9. 57 times 5 is 35. Carry the 3. 25 plus 3 is 28. So you get 285 degrees divided by 9 will be the answer. You could use a calculator at this point or do it brute force. All right, brute force is still useful. Maybe throw some zeros in there just to get rolling. All right. And proceed. All right, how many 9s could you fit into 28 roughly? 3, right? So that's 27, the difference is 1. I'm doing short division. 9 goes into 15 roughly 1 time, decimal point. The difference of 15 and 9 is 6, right? 9 goes into 60 roughly, 7 times would be 63, that's too much, so it would be, 6 would be 54, good. 54 and 60, the difference is 6 again, so this is going to repeat. Right? What you should get is, if you're getting an exact answer, 31.6 repeating degrees. If they ask you to round, and I didn't specify in this particular problem, you might round it to the nearest degree, in which case you'd say it's about 32 degrees Celsius. Right? That would be, as you can see, a fairly hot day, right? 89 is not really that comfortable, right? 20 degrees Celsius is more like room temperature. That's what's going to happen here. All right, now you use a different formula. If you're starting with Celsius, notice there's no parentheses here, all right? You do things mostly intuitively, but you're going to write the number 20 in here. And therefore, this would be 9 over 5, the reciprocal of 5 over 9, times 20 over 1. You do that portion of it first because it's multiplication, and there is no other condition being specified. Again, you could just do brute force top times top, bottom times bottom, and then straighten it out as before, after the fact. In this case, it would be practical to try to simplify it first. So, the common factor that makes both 5 and 20 is 5 itself. So as long as you're simplifying things that it's 1 below the line and 1 above the line, either diagonally or directly, then simplify first. 5 divided by 5 is 1, and 20 divided by 5 is 4. It's just 1s in the bottom, so it's superfluous, you don't have to worry about it. Then it's just 9 times 4, which means that it's 36. 36 plus 32. So, 6 and 2 is 8, and 3 and 3 is 6. This ends up being exactly 68 degrees Fahrenheit. Okay? That makes sense, right? 20 degrees Celsius is room temperature, right? So 68 degrees is room temperature, basically. Moving on. Okay. For 8, this is, I think, another one of those that I stole from the MyLab problems. Let's see. Given a volume of water is 2,304 cubic meters, right? Use the reference table below to convert to mass in metric tons. Now, these are good relationships to know, right? It just so happens that 1 cubic centimeter is equivalent to 1 cubic meter, right? I know that this is a volume, right, and that's normally what we consider a solid volume, right? And this is a volume that is a liquid volume. But it so happens that these translate to a certain mass. Right? It happens to be a scientific definition of what water is at standard, standard temperature and standard pressure. Right? Anyhow, 1 to 1 to 1, right? And therefore it would be 10 to 10 to 10 if you would up it to, 10 times as much, 100 times as much. If you did it so far as to say, well, what is it? If it's 1 to 1, right, in any of these, right, then it would be 1,000 to 1,000. There's a little sneak that you could pull here, a little sneaky trick here, if you remember, right? 1,000 grams just so happens to be how many kilograms? 1 kilogram, right? So you have a conversion factor relationship, it's just obscure, is what I'm getting at. If you're taking advantage of the fact that 1,000 grams is exactly 1,000 grams is exactly 1 kilogram, you can convert from a cubic centimeter directly to a kilogram. There is an obscure conversion factor, right? Why would you want to do that? Because eventually you would have to answer the question, you'd have to convert so many kilograms to so many metric tons. Right? Metric tons, just be careful, they're not the same thing as the imperial tons that we have. And to distinguish one from the other, what has been decided upon by somebody is that metric tons is lowercase t and imperial tons is a capital T. Notice that the spelling is more the British tradition, interestingly, T-O-N-N-E. Right? Well, perhaps it's French, I might even say. Whereas in the United States, we spell things often shorter. Right? Somewhat spitefully, sorry. So you can thank Noah Webster for things like that. Anyhow, let's do this conversion. We'll convert this cubic meters to kilograms directly, all right, because we can. Based upon this obscure relationship, right? Cubic centimeters, okay. You know what, there's another step in here and I'm getting ahead of myself. I don't really have the room, unfortunately, so I'm going to have to do this a little bit silly, perhaps. Alright, give me 1 minute. Alright. let us start with the basic relationship that we know. All right. We're going to convert cubic meters into so many cubic centimeters. Right? We kind of did this before anyway, but I'll reiterate. Here's a cubic meter in theory. Right? It would be 1 meter this way, 1 meter this way, and 1 meter this way. And independently of each other, 1 meter would be by definition 100 centimeters. So it's 100 by 100 by 100. Right? If I calculate the volume, right, of 1 cubic meter in terms of cubic centimeters, I would in fact have to multiply 100 times 100 times 100 instead of 1 times 1 times 1. And then we have what we had before, which is this. 1 followed by 6 zeros, right? All right. We need this conversion factor from before, essentially. Oh, sorry. All right. Now, because I need the space, I have to erase that, sorry. All right. So, if I have this figure, 2304 cubic meters. The first thing that I can do is convert that to cubic centimeters. Right? So if I want them to cancel, if I want meters to cancel, I'm going to strategically put the conversion factor meters cubed down here. Right? And that will force the numbers to be in a particular place. So if it's 1 cubic centimeter, it is the equivalent of 1 million. 1 cubic meter is the equivalent of 1 million cubic centimeters. Then that would be on top and this would be on the bottom, right? You could just do your cross cancellation and spit out the answer, or you could build in separate little pockets here each of the subsequent conversion factors. I would love to do that. Unfortunately, I'm kind of a dodo and I put this block here too. Maybe I'll write it down here. It'll be a little bit more satisfying. I'm just rewriting the same thing in a better location. Humor me one moment. You might be a little deterred and go, those are pretty big numbers they put. All right, don't be. All right, if you're careful, if you're strategic, you can spare yourself a lot of trouble. Right, by writing this in the correct sequence first. In other words, set the controls on the machine, and then you can have the satisfaction of crossing out a lot of stuff at the same time. All right. Now, this information that we took from basically earlier problems, that this is a relationship 1 to 1,000,000. All right, will accomplish cross-canceling cubic meters. I want to convert cubic centimeters to so many kilograms. All right. So we'll see what we can do. I'll put that in blue just adjacent here. 1,000 cubic centimeters down here will essentially cancel this cubic centimeters that is left over from the last conversion, and that's equal to 1 kilogram. All right. And then the answer is actually answering for metric tons. So I'm going to take this next one, and I'm going to rig this last part here. Hopefully this green will be visible. Is that okay? Looks like it's all right. All right. 1 metric ton is what I want. So it's a lowercase t for a metric ton. And that is, again, 1,000 kilograms. Okay. You could have done this piecemeal, as I was alluding to, or you can do it, which I think is maybe more satisfying once you get a certain level of comfort. Rig it like a machine. You're setting the controls on the machine before you turn it on. All right, and here's what's going to happen. All right, this, because it's down here diagonal to that, is going to cancel those units. All right,
centimeters cubed will be canceled by this down here, and kilograms will be canceled by this down here. Now you could do top times top times top times top and write it on the end if you'd like. And then similarly, you could do bottom times bottom times bottom times bottom. Or you could take advantage of some mental math skills. And the mental math skills would say you could cross out things, right, that have a common factor before you multiply, right? Which is, especially when you have things with a lot of zeros in it, very satisfying, right? Notice that this is just a relationship of 1 here and this is a 1 here. How many zeros are in 1,000? Right? How many zeros are in 1,000,000? 6, right? If you essentially, because 1 is above the line and 1 is below the line, if you're looking for a legal reason why you can get away with this, all right? It's like dividing, right? I know that this is multiplication, but if one thing is above the other, ultimately you're dividing them. That's the legal reason why you can get away with this. If you don't want to think about it, you just want to employ the shortcut, that's fine, all right? You see 3 zeros here? Cross out 3 zeros here, all right? And then it just so happens that there's another 1,000 over here because of the relationship of kilograms to metric tons, right? There's another 3 zeros here, below the line, and there's another 3 zeros here, above the line, right? That leaves you with a much easier calculation, and here's what happens. 2304 times 1 doesn't change it. Times 1 doesn't change it. Why do I say 1? Because that's the only digit left over after the cancellation. Times 1 doesn't change it, right? So you would have 2304 above, and then 1 times 1 is 1 times 1 is 1 times 1 is 1, and that would be 1 on the bottom, all right? What is the only unit strategically left over? The one that we're looking for, all right? So it turns out that 2,304 cubic meters actually is 2,304 metric tons as well. Right? That's the way the math works out. Okay? This can be a little arduous again if you don't have a lot of practice. That is to say, if you don't have a lot of experience, you might be, a little timid and not putting your toe in the water. All right? But I'm telling you, when you get comfortable with translating conversion factors, this is the way you would love to go because it simplifies everything. You could do a lot sort of without thinking too deeply. You could do things automatically, right? Especially in a chemistry class. All right. Next question. This one I definitely stole from my lab assignments because I felt, although it was given to you and you could figure it out, it would be worth the time to explain it. So I tried to. Let me take a sip of water. That happens too many times. Okay, determine the quantity of mass that would be needed to perfectly balance. All right, without any information, any background in physics, just realize this: you want to balance something. All right, if you want to balance something, or if you want to balance essentially, if you're balancing, it is implying that there's two things involved here. So you could start with this without any other information. Something has to equal something else, right, in order for there to be balance. Right? You don't need to know anything about physics. You just need to know that if something is balanced, then some first thing has to be equal to some second thing. Okay. Now, it just so happens that there are other little intricate components to this, right? This is a seesaw, right? And there's a point at which it will tilt one way or the other, right? If you want it to be stationary, perfectly level, all right, then it would in fact have to be balanced. Now, let's try to incorporate the pieces that we have here, all right? there is a 5 kilogram mass on this side, and we're trying to figure out, well, what would this have to be as a result of that? If it was exactly in the middle, all right, then it would need to be 5 kilograms here and 5 kilograms there. The weight of the one child on this side would have to be the weight on the opposite side. I should really say that mass would be more appropriate. Anyhow, notice that whoever designed this problem is being a hooligan. You know, they said, well, it's kilograms, and then over here they put it in regular grams, all right? Let us stick with what we're given first, all right? We're given things that are the units that are really the more traditional units for a problem like this. Kilograms is the standard for a mass, and meters is the standard for a length, all right? Yes, they mess with you and they put centimeters here and they put grams here, but we could always convert later, all right? Anyhow, we have two things to incorporate, all right? A mass and a length, all right? That's on this side of the pivot fulcrum here, all right? And then we have this unknown mass and we have a length. Again, if you had no background in physics at all, you might reason to yourself, well, there's only, to incorporate these things together, you know, to make them one autonomous thing, all right, I would not be allowed to add them because one is a different unit than another, right? This is a kilogram unit and that's a meter unit. So you can't add or subtract like terms. That means that if you have this many choices, you have addition, subtraction to choose from, or multiplication and division to choose from, you can only add or subtract things that are like, right? You could multiply virtually anything though, right? So you might multiply these two things, right? On this side, you have a mass and a length. So we'll multiply those two things, all right? If again, we're trying to make something balanced though, they would have to have the same features over here as well. So it would be a mass times a length. All right. So what does that mean? All right. Well, it would be 5 kilograms, all right, times 2 meters on this side. And again, because we have to have consistency, we would have to have something else over here, the second thing, as so many kilograms. I know that it's telling me grams, but we convert it later. All right. And then a certain length as well, right? Certain meters, right? There's a better way to explain this, but I'm trying to basically tell you how to do this independently of this information, because this information about torque is not given to you at all right? Just reasoning it through pure logic, all right? Balance is comparing two things, all right? If on this side you have these two things, all right, what can you actually do with them? You can't combine them by adding, but you can combine them by multiplying, because you don't care if things are like or unlike when you're multiplying so much. Okay, so we're going to go that route. All right, that's the logic behind it, really. All right, anyhow, let's do a little bit of converting. We want this, since this is meters here on the known side, we would want the opposite side to be meters as well. 400 centimeters is how many meters, all right? If you're converting from centimeters to meters, you're moving this way along the diagram, the horizontal diagram, right? So it would be dividing by 100, basically. You're moving your decimal point twice this way. So, right, you would end up with 4. So that means the number 4 would be here, all right? Then there's the mysterious unit, all right? If you see 1, 2, 3, 4 parts here, all right? A kilogram, meter, unknown kilogram, and a known meter now, because that's really 400 is really 4. You have the majority of information, and in theory, you could rearrange it algebraically to figure out what this unknown mass is. Again, it's going to be in kilograms to start with. All right. I'll write it over here because I'm running out of space. what is 5 times 2? 10, right? And then you have these leftover units, kilograms and meters here. So I'm just going to not throw them away. I'm just going to write them next to each other. And then on the opposite side, put this in black, we have 4 times an unknown amount, which is what we're really solving for. In algebra, we have a tendency to use an x or something for something that is mysterious. So I'll put 4 in front of x because that's better etiquette, and then the same units, kilograms and meters here, right? When you're solving algebraically, remember you perform opposite operations. That means that the numbers involved have to go to the opposite side of the thing that we're solving for. In this case, this is the question of the actual number for kilograms. It has a coefficient apparently of 4 because of the meter unit, all right? I'm going to move the 4 from here over to here, all right? Divide by 4, cancels, divide by 4. If you straighten out just the numbers alone, 10 divided by 4, this will give you the decimal of 2.5, right? If you're worried about the units, you could reason it through this way. I know that this is a unit and we tend not to worry about them, but if it's the same exact units here and here, then this would cancel this via dividing it as well, kg, kg, and then eventually this would cancel this via division as well. And that leaves you with just the thing that you're looking for, which is actually x, which is actually the mass, right? Now bear in mind, this is the number, right? And the number was originally in kilograms because that's what we started with. So this mass is in fact 2.5 kilograms. If they're asking what it is in grams, you would now have to convert that as an afterthought, right? The relationship of kilograms to grams is 1 to 1,000. So you'd be multiplying by 1,000. The effect is that the decimal point would be moving 3 spaces. This should be 2,500 grams is the actual answer. Right, now, that's me kind of dancing around a little bit, trying to explain how to do this without any information about physics really, all right? It's just the pure logic of we're balancing. So there's something on this side of equals and then there's something on the opposite side of equals. What's quoted to us? An amount of mass and a length, all right? And then an amount of mass, granted it's in a different unit, and a length, granted it's in a different unit. If I'm trying to make things balanced, then there has to be this consistency. Kilograms here, therefore kilograms there. Meters here, therefore meters there, right? And then I'm just manipulating it algebraically to get to an actual number, 2.5. And that is a complete absolute afterthought, converting so many 2.5 kilograms into the unit that was given. That's, again, me dancing around trying not to explain physics. Now, I will do it the other way, which I think is a little bit more sympathetic. You know what the answer is, right? This is the kind of problem that you get in a physics class, right? And it would help if you happen to have ever seen physics in your life, then you might have heard of this and seen this type of drawing and done this type of problem. This is a Greek letter known as tau. And tau stands for torque, right? What is torque? It's essentially the force of rotation, right? It's a little bit more complicated than standard force. Standard force is 2 things multiplied. It's mass times acceleration, right? Which is often abbreviated as ma, m times a, right? There's different types of forces, right? This is just a general Newtonian way of writing it. Force abbreviated F, mass abbreviated m, acceleration, change in velocity, change in speed, if you will, in a specific direction, all right, is abbreviated A. A weight is not a mass, right? A weight is in fact another type of force. So you might put either W or you might write a subscript W, right? And it's dependent upon, again, the mass of something, all right? But then because it's a downward force, it's dependent upon gravity. So it would be G is the specific acceleration. G is 9.8 meters per second squared. Right? Anyhow, if you're hoping to balance something, again, there would be two sides involved here, right? Something has to equal something else, again, if it's balancing. Right? This first side and this second side. Well, it's really the torque that has to be balanced on this side, and then the torque balanced on this side. Now, what is the torque? The torque is a force, so it will be this much of a formula, one way or another, MA or MG if we're talking about weight, times a length. That is how long this lever is. All right? Okay, where the force is applied is how long the lever is. All right, so you would have on this side of this balancing act, literally balancing act, right? An M, a mass, and the acceleration of G, which is dependent upon Earth's gravitational attraction, which is negative 9.8, and then this length here. All right, and on the opposite side, you would have those identical conditions, a mass, G, and the length that is on that side. All right, so what you will do is input what you've known described here. All right, it's overcomplicating it only for the reason that there's a G involved technically. All right, but you would have 5 kilograms here. And you would have 9.8 multiplied by that, negative technically, meters per second squared if you wanted to involve the units. And then you would have the length of this lever, which would be 2 meters. All right? And if you straightened out all of that, it would be 10 times negative 9.8, which would be what, 98? And then you can analyze what the units are. On the opposite side, before you actually do the multiplication though, maybe you could spare yourself a little bit of work. All right, on this side, we're solving for the mass. We'll just leave it as M then. And then you could input the same figure. All right, the gravitational acceleration is the same because this is not on Mars, this is on Earth, in both places. All right, times 9.8 meters per second squared. And then the length here, it's in centimeters. You would have to convert that to what it is, 4 meters, right? And you have all of the same numbers that you needed, all right? What I'm getting at is that you're going to produce the same result whether you understand the physics or not, all right? But it would help just for the sake of confidence, and that's really what the deterrent is. A lot of times a person will get a question wrong because they're scared, You just have to talk yourself out of it a lot of times, and in the position of teacher, you must talk your students out of it, right? Don't let them get scared, right? Because then they'll make a mistake, right? Anyhow, look what you have here. You have essentially 5 times 9.8. I'm just taking the units out for a moment. And you have mass, which I'm just going to keep in black because that's what we're looking for, times 9.8 times 4. All right. If you just pay attention to basically the essential numbers involved and the thing that you're looking for in this case, look what is the same on both sides. It's technically negative 9.8. Without doing the actual multiplication, which I'll just replace with multiplication dots for a moment, you could, if you realize that this is just multiplication here and just multiplication here ultimately, you can reason to yourself that, well, this is identical here and here, so they would cancel naturally anyhow. That's why you can get away with not understanding anything about torque, right? And nothing about forces, because you would not need to know that gravity, the acceleration due to gravity is 9.8 meters per second squared, because it would effectively cancel anyhow, right, if you're balancing something. And that leaves you with the essential numbers involved here, which is 10 and the number 4. Right? And then you have a one-step algebraic equation. I just like it in this orientation, personally. If it's something times that mass that we're looking for, 4 times that, then to solve this one-step equation, I divide by 4 here, and I divide by 4 here. And I nonetheless have this relationship of 10 to 4, which is really 2.5. You just have to remind yourself, this is the only thing that is a little bit trickier, is that because you have working with kilograms on this side, this would have to be kilograms you would assume to begin with, right? But they don't want that. They want grams. So then you would have to convert this to 2,500 grams. Okay? Sorry if that is too much of an explanation. It just seemed like it was worthy of taking the time. I'm just burning through my data here. Okay. All right, moving on. For section 7.4, dimensional analysis, conversion to and from the metric system, right? You see that there's a blend here of imperial units, gallons, pounds, miles, and the metric units, liters, kilograms, and kilometers, right? There's always, these are rounded, all right? Because you're converting from one system to another entirely, all right? Just realize that these are rounded, okay? If you're going to convert 2 gallons to so many liters, just incorporate the appropriate conversion factors that we have here. Remember, the conversion factors are written in the style of a little equation here. But when you're doing the work, write it in that sort of sequence. The thing given times the conversion factor will spit out what you actually want. So if you want to cancel gallons as a unit and end up with liters, because that's what they're asking here, liters must be above the line and gallons must be below the line. That will force the numbers involved, 1 and 3.8, to be in these specific locations. 3.8 liters is 1 gallon. All right. This cancels this, and then it's a matter of 2 times 3.8. All right, which gives you what? 7.6. Just verifying here. 16. Yep, 7.6. 7.6 liters. Sounds like car engines, right? No, not a car per se. That's quite a hefty car. In terms of an engine. All right. Next one, kilograms to pounds. All right. If you're starting with kilograms, write that first. 5 kg. Write the appropriate conversion factor immediately next to it. You don't have to put it in parentheses. I like to do that because it is isolating and drawing attention to it. Right? That's the tool, you know. It's written in this orientation. 1 pound is less than a half a kilogram. So if you want to cancel kilograms, put kg on the bottom. If you want pounds left over, libra pondo on top, lb. Right? That would force you to put the numbers 1 and 0.45 in these respective locations. 0.45 to be official. Right. Now, that will cancel the units, so you will definitely get pounds. What's going to end up happening is, if you treat this like fractions, is that you get 1 times 5 is 5 on top, and 1 times 0.45 on the bottom. You can make your calculator do this, so you could divide it. All right. What you should get is 11.1 repeating, if you want to be very exact. All right. 5 divided by 0.45 is 11.1 repeating, right? All right. So that's how many pounds it would equate to. Next one. 80 miles is how many kilometers? You would write 80 first. Miles is abbreviated MI. And the conversion factor, cancel, put miles down here, put kilometers above. 1 mile is apparently 1.6 kilometers approximately. All right, and this will cancel miles. justify that you have kilometers left over as a result of that cancellation, and then it's just basically 80 times 1.6. All right, what do you end up with? You should get 128 kilometers. Okay. Okay, now into geometry. Come on. All right. This is good to do with a highlighter or something. Green and maybe blue. Oh, red's easy to see. Okay, this question is, using the diagram above, what is the intersection of the ray FB and the ray EB? Remember, rays have a starting point. Right? But no endpoint. They're infinite for all intents and purposes. Right? And they're symbolized like an arrow, like so. Let's see. When you're talking about an intersection is asking you, which is abbreviated as a sort of a horseshoe shape, about the overlap only. Okay? If I were to write this less verbally and more symbolically, you would see an arrow over FB and an arrow over EB, and in between them the horseshoe. Okay, so let's just highlight in the drawing FB and then EB respectively. The first initial is F here, right? So this is the starting point, right? And we need another letter just to give it a general direction, but because it's a ray, and that's what the arrow is indicating, this would blow past it in this direction. I'm going to over-exaggerate this. I'm trying to highlight basically this ray. This, even though it goes through E, it goes through beyond it. We just use this other letter basically to give it a general direction, but it goes beyond it. All right, and now just to distinguish it, I'm going to use a different color. EB is the first letter quoted to you here. We're talking about a ray again. So this is the starting point now. All right, and again, we use the second letter just to give it a general direction. E is first, that's what you start. B is second. You do go through that, but you blow past it. All right, and then you have an arrow headed off in this direction. All right. Now, what we're looking for, since we're talking about an intersection, is the overlap of these two things only. Right? If you have it highlighted as such, right, you will notice that the extent to which they overlap is basically from here to here. This is where they overlap. Right? So what initials are involved from this point to this point, literally? Right? It would be E to F, right? So we have that to start with. And then what type of thing do we have? Well, if it starts here and it ends here, it's no longer a ray, right? What you end up with is a line segment, right? That also incorporates the endpoints themselves. So you would put a simple line like this to symbolize that above point E and F. You can have it reversed. I don't think anyone would get mad at you. It means the same thing, right? My intuition is to do it in alphabetical order. Right. So you have the intersection of these two things is the line segment EF. It's the extent from here to here, and nothing more. Because that's what they have in common. Right? An intersection is what is in common, and therefore it's an overlap. Okay. When you do something like 14, You need this diagram, firstly. There's different line relationships to be aware of, all right? And there's more than one way to do this, but to me the easiest way to do this is to incorporate just two relationships, right? I'm going to just sort of list them here. You've probably heard of vertical angles. That's one possible relationship. Let's see. Supplementary angles. Technically complementary as well. That's not going to be involved here. All right. Alternate interior, alternate exterior, and then corresponding. It would be good to know which are which. That is to memorize certain relationships. And you would need to do that according to the definitions. All right. Interior means inside the parallel lines. All right. Alternate means opposite sides of a transversal. All right. So if you have alternate exterior, that means outside the parallel lines. And alternate is still opposite sides of the transversal. They're the same. All right. Corresponding angles are the same side of the transversal. All right. But one inside, one outside parallel lines. All right. Supplementary means that they are two things that add up to 180 degrees. Vertical angles are directly across from one another. Lines that cross. All right. Complementary is you add up to 90. All right. Anyhow, you don't need to incorporate all of these. I got away with just using two myself. All right. You are asked to find angle 8 here. All right. And you're only given angle 2. All right. These things, angle 2 and angle 8, are on the same side of the transversal. So I immediately gravitated to a corresponding relationship. The thing is, these themselves, angle 2 and angle 8, are not corresponding, but I can use corresponding relationship to my advantage. What is corresponding is this. Angle 2 is corresponding to angle 5, and that happens to be adjacent to angle 8. All right? Anyhow, these are all on the same side of the transversal. One angle here is outside the parallel lines. Angle 5 specifically is on the inside of the parallel lines. Therefore, angle 5 is 26 degrees because these are corresponding. Then, if I'm just zeroing in on angle 5 and angle 8 for a moment, if this is 26 and this is angle 8, all right, they have a supplementary relationship. They're adjacent angles, that means they're butted up against one another, all right, and they're part of the same straight line running this way. They're just cut up in this arrangement, all right. That means that the balance of 26 degrees, in tandem with the balance of 8 degrees, right, angle 8, should equal 180 total. the bottom line is that you're going to subtract 26 algebraically from both sides of this, and then angle 8 is equal to the difference of 180 and 26, which is 10, that becomes 7, this is 4, it's 154 degrees. Okay, you really just need to know, in this instance, corresponding relationship and supplementary relationship. All right, these other things exist, and I would keep them, don't throw them away. All right, but they're not, you don't need them in this case. All right. Next problem. All right, using the formula, this is Euler's equation. One of Euler's equations, it's famous for quite a few. At least 2 or 3 of them. So, okay. The sum of the measures, that is the total angles can be calculated from number of sides. Right? As long as we're talking about a regular polygon, right? A regular polygon would be equiangular, okay, which means all of the interior angles will be the same. All right. The sum of the measures of interior angles of an n-sided regular polygon, I really should have put that. All right, determine the, well, yeah, I guess they would be the same. Yeah, it's not important, so I'm obsessing now. All right, determine the total for that of a triangle. How many sides does a triangle have? 3, all right. If it's not a regular triangle, all right, pardon me, if it isn't an equilateral triangle, it doesn't have to be. You can still get the total, right? Even if you don't know what the individuals, how they're divvied up. All right, 3 minus 2 would be 1. 1 times 180 means that you would have 180 degrees total, which is the definition of a triangle's angles. All right, 180 degrees. That is still useful to go through this exercise and to be familiar with this formula when you're answering the subsequent question. It's a different shape, granted, but you will incorporate this. Right. So I'm going to scoot this up just a wee bit, and I'll try not to obscure the formula. Let me emphasize certain things. Now you're given a regular polygon. It is a hexagon, and it's just drawn badly. If it's regular, it means that the angle here, and the angle here, and the angle here, and the angle here, and here, and here are all the same, right? What you might call equiangular. All right. So we can use this formula to figure out the total first, and then divide by the number of angles that you would have as interior angles. All right. So given what is true about regular polygons, that they're equilateral, it means all the sides are equal, and equiangular, which is more important in this case, what must be the exterior angle here in the red question mark? All right. Let's figure out what the total is first using this formula. All right. It is a 6-sided figure. It's a hexagon. So it would be 6 minus 2, and therefore it's 4 times 180. 0, 32, carry the 3, so it would be 720. 720 degrees total, right? Because it is equiangular, that is to say, because it is a regular polygon in this particular case, one can assume that each one of these interior angles is identical. They're not divvied up differently. So you're going to divide by how much? 1, 2, 3, 4, 5, 6. All right. 6 goes into 7 one time with 1 left over. 6 goes into 12 exactly twice, and into 0 times. That means that the angle here is 120 degrees, as all of the others. That's 120, 120, 120, 120. But now we can answer this question. All right. These things are 120 and an unknown amount. This forms a straight line. A straight line from here to here is by definition 180 total. So if you wanted to figure out the balance, you would subtract 120, right? And what do you end up with? 60 is what question mark equals. Moving on. This one I had to draw the picture. This is a little verbose. I really should rephrase this, but I tried to be thorough more than concise. Okay. And I stole this from one of your questions too. Whereas congruent figures are completely equivalent in terms of their sides and their side lengths, right? Congruent figures are basically identical figures in terms of side and the angles inside. Similar figures are proportionate, right? Meaning that they have corresponding sides. They're not the same length, right? They're not equal, right? But they might be larger or smaller by some consistent factor. They're proportionate is the best way to refer to this relationship, right? Taking this into consideration, use shadow reckoning. It's basically write a proportion. Equation, right? To indirectly determine the height of a tree in the diagram that follows. So here is the diagram that follows based upon description from my lab. All right, this is me being, when I wrote this, this is out of my mind. I thought of a happy sun, right? Looks like an anime sun now. And on the box of Raisin Bran, it's always holding 2 scoops of raisins. So enjoy 2 scoops of raisins and also this proportionate shadow. Waka waka. Alright, so anyhow, ignore the sun. It's just casting a shadow, really. Alright. These figures are, to me, with the way that the answer works out, you'll definitely get the correct answer, and I'll tell you what it is in a moment, but I didn't like the way that they chose this, the numbers involved here, because it seems like the height of the tree is rather unusual. Anyhow, you see basically proportionate triangles. There is a smaller triangle, and which they have superimposed inside a larger triangle. The reason for that is because it makes the picture more concise. It's a right triangle. It frees up some space when you're drawing this, right? But it also shows you that the angle here is consistently the same, right? So it is without question that they are proportionate, right? You could draw them as separate triangles if you want, one big, blue one and one small red one adjacent to each other. But the point is that they are proportionate. They're not the same size, right? But are proportionate. Therefore, you could write a proportion equation. What is a proportion equation? A proportion equation is firstly an equation, so you'll see an equal sign, and it's taking advantage of these equivalent ratios, right? That is, the side dimensions involved here are not individually equal, but overall, the ratios are equal. When things are proportionate, it means that they have equal ratios, which is, again, a glorified fraction, right? So if you have essentially a fraction set equal to a second fraction, realize that you have 4 parts to work with, right? As long as you have 3 out of 4, that is to say the majority of the information here, you could always, via algebra, figure out what the missing chunk is. Right? Just be consistent. When you're doing this, all right, when you're trying to decide how the ratio is divvied up, I would do this. I would make the height the top figure, the top dimension, and the bottom of any one of these, the shadow length. All right, be consistent. Okay, so first of all, what is the height of the tree? We don't know, so we're just going to call that h here. All right. What is the shadow length of the tree? All right, it's 120 feet. Right? You should make sure that the units are all the same too. Right? I'm dedicating this first ratio to tree dimensions. Right? And therefore I will dedicate the second ratio to the person's dimensions. Just be consistent. If you've made the height the top figure, then it must be the height here. How tall is this person here in the drawing? 5 feet. So I'm going to put a 5 here. What's their shadow length? It's 8. Right? So you have an 8 here. Right? Now you have a proportion equation. And how do you solve proportion equations? To solve, you cross multiply. Right? So let's do that. What is the abbreviation for 8 times h? It would be, in good etiquette, it would be the 8 in front of the h. Good etiquette of math, if you will. All right. And then on this side, I'm going to cross multiply these diagonally. And it would be the outcome of 5 times 120. I am purposely not multiplying them. It isn't wrong if you do. As a matter of fact, I think that would probably be the more intuitive thing. But the reason that I'm not multiplying is because I'm trying to do this without a calculator. So I'm trying strategically to make it easier on myself. So without producing a larger figure, even though you can, all right, I'm going to write it like so. I have one side of my equation now, the two things combined, 8 and h, and a second side, quasi-combined because I didn't actually multiply them. Just put a dot to signify that they would be. Okay, now, just trying to avoid, again, using the calculator. You don't have to. Right. I'm going to manipulate this by moving the 8 over here. Right. The opposite of multiplying by 8 is to divide by 8. There's a cancellation effect by design on this side because I'm looking to solve for h. And if I did that here, then I'm obligated to do that here. Right. What does that mean? It means that this is what I'm working with. That h, the height of the tree, is going to be the outcome of 120 times 5, all sitting on top of 8. Now, because this is in factored form, this is, mind you, an over-explanation, you can, if you want to, blend together these two parts. Right? That is, you could do the division here. You could do the simplification here. If you recognize that there is some relationship between 120 and 8, you could simplify before you multiply. This is, again, me trying to not use a calculator for my own sake, not that you have to do it this way. All right? It just so happens that these are both made of the factor of 8. How do I know? Well, I'd actually divide these. 8 divided by 8 is 1. All right? 8 into 12 is 1 with 4 left over. 8 goes into 40 exactly 5 times. That means that the height is really 15 times 5, and therefore the height is really this somewhat suspiciously large tree, 175 feet. Pardon me, just 75 feet. All right? Whether you did it my way or you did it just, brute force with the calculator, that's fine. That's, I wouldn't say it's brute force, it's, with the calculator. You would get a large number here, divide by 8 as an afterthought, and you get the same answer, 75 feet. This came from, I want to say, my lab, right? How many trees do you know, though, that are 75 feet tall, all right? It isn't impossible. The redwoods, the sequoia trees, right? They grow quite large. They might even be larger than that, right? You can drive a car through the base of them, they have in some cases, all right? But that's an unusually large tree. Nonetheless, that's what you would get based upon the numbers that are involved here. I just was suspicious of that, All right, 18, bless you, is the Pythagorean Theorem you would need to use first, and then to calculate the area and the perimeter of the shape. In this case, it would have to be a triangle. I'm trying to confine myself to so much space here.
use the Pythagorean Theorem, a squared plus b squared equals c squared, which you know is specifically for right triangles. You can't apply this to other things. All right, you're not without employing some trig functions. To determine the area and the perimeter of the triangle below, this one. If we were going to calculate the area of any triangle, and then the perimeter, there are some formulas that we would also have to incorporate. I'm going to move this mouse because it's kind of annoying. All right. The area of a triangle is most concisely writ as base times height over 2. Right? Divide by 2 because it would be the same as a rectangle cut in half. The perimeter, there's no fancy formula for this. It would be 3 sides independently added together. So I'm using the letters that are here. A plus B plus C. Let's get this. We don't know all of the dimensions though, which is why we have to use the Pythagorean theorem first. All right. There's a couple of things that you must remember. All right. The things that are perpendicular, the dimensions that are perpendicular, this box would signify that, right, are legs of a triangle. Across from this is the hypotenuse. The reason that I'm belaboring this point is that when it comes to substituting values into this formula, the legs are interchangeable. You can call one A and the other B and vice versa. But the one thing that is non-negotiable is the hypotenuse, the C value. So in this formula, you would have to really put 25 here. Right? A, I'm just sticking with the labeling, would be a 20 there. Right? And the thing that you're looking for is B. Okay? So, just to do some of the work over on the side here, if you have essentially 20 squared plus B squared equals 25 squared, I would, unless you have in your mind the formula already rearranged, and with enough familiarity with this, you would do that. Simplify what you can, do the arithmetic before you do your algebra. 20 squared is 400. So this would be 400 plus b squared, and 25 squared would be 625, I believe. Okay. Now, since you can't do anything more to simplify, drag 400 over here via algebra. You've done arithmetic, the foundational techniques. Now you would perform algebra, the slightly more sophisticated techniques. Arithmetic says do the operations as they are written. Algebra says if you're going over equals, as you would have to in this case to solve for b, do the opposite operation. So if this is positive, you're going to subtract 400 here and here. That leaves you with what you're looking for, b squared at least, right? And then subtract 625 minus 400 is 225. And you could use a calculator if you want. It turns out that this is a nice whole number. This is a rational number. The thing is, it's the square of this that's 225. We want just regular b, not b squared. So we would again have to employ algebra at this point. What is to cancel? What is the opposite of squaring something? To square root it. And if you did that here, you're obligated to do that here. Essentially, that cancels this operation and leaves you with just b, which is what you want. The square root of 225 is a nice whole number, 15. Right? So, now we know that this is 15. Right? Now we have all 3 dimensions, we could calculate the area and the perimeter. The only thing is that in the area formula, one of the dimensions is called height instead. Right? The height dimension is really the A dimension. In this case, it's labeled as A as opposed to H. So that means that this is really 15 times 20. And if you want, you could simplify as if you were dealing with factored fractions, right, first. There's no sin in doing 15 times 20 and then dividing by 2. That's perfectly legit. But if you're trying to do it, mentally somewhat, this is what you might do. Recognize that there's a relationship between 2 and this other even number 20. That would be half as much. So therefore, the area should be 150 as the magnitude. And in terms of the unit, it's inches
times inches, so it would be inches squared always for an area. 150 inches squared. All right. Then when you are finding the perimeter is the distance around something. All right. So you just have to incorporate 20, 15, and 25, and add them together. All right. 20 plus 15 is 35. 35 plus the leftover is 60. The perimeter would be 60 inches, first degree, because even though we're talking about a two-dimensional figure, we're just adding. So it's inches plus inches plus inches. All right, so you get a one-dimensional sort of measurement here. Inches is the distance around. Okay. Next one, area and circumference. Find the area and the circumference. Because this is going to incorporate pi, just realize that we want to try to hold off on substituting the number 3.14, what have you, to whatever degree of precision, until dead last, because it would force us to round. Right. So we're going to calculate an area and a circumference. Circumference is basically the perimeter of a circle. It's not quite the same thing because the circle doesn't have sides per se, it has an edge, or the extent of its radius, outward. The area formula for a circle is area is equal to pi, the irrational number, times radius squared, right? The circumference formula is pi, there's two different versions. There's pi times diameter, or a diameter broken into two, which is pi times 2 times r. All right, and since they gave us a radius here of 10, you might as well just go with this incarnation of the circumference formula. So, the number 10 is a nice number because it will just allow us to move a decimal point to and fro. The answer has to be rounded to the nearest hundredth. Again, round, dead last. All right. So if I put a 10 in here, I follow the order of operations, which implies squaring first and then multiplying by pi. That means that realistically you would have 100 times pi. Right? If pi is 3.14, whatever it is, into infinity, 159 something, then multiplying by 100 is going to have the effect of just scooting the decimal point over two spaces. Right? And then it would be 314 and change. If you're rounding to the hundredths place, that's where the 5 is sitting, right? You could use a calculator to verify this. And therefore, based upon 9 it being adjacent to it, your answer would be about, you should use a squiggle equals, all right, 314.16, all right, centimeters squared because it's an area. All right. When you calculate the circumference, remember that's the distance around something. In this case, it's a circle, so we call it circumference instead. You would embed the, substitute the same figure 10. The diameter would be 20, but this would be essentially 20 times pi. All right? If pi is 3.14, then twice as much would be 6.28, whatever and change. All right? What you end up with is, after you're rounding, is 62.831, so it'd be about 8.3. Right? And since it's a circumference, it would just be centimeters. 62.83 centimeters, degree 1. Okay. You know what? I think I have erroneously attributed this formula to Euler. You know what? I'm sorry, I'm scooting all over. But n minus 2 times 180, I don't believe that is, I'm not sure, I gotta look that up if that's his or not. It's geometry, so very likely it is Euclidean, you know. I shouldn't really give things to people that they did not author. This is Euler's polyhedron formula. Euler was quite brilliant, but I don't know if he invented that sum with the interior angles formula. Or discovered it. Right. Anyhow, find the number of faces of a polyhedron that has 13 vertices, those are the corners, and 15 edges. Right? If you have a shape, the edges are the sides, basically. Just from the perspective of 3 dimensions rather than from the perspective of 2 dimensions. Consistently, all right, this relationship seems to hold, right? If you subtract these and add that, you will get 2, no matter what polyhedron you're dealing with. Remember, polyhedron is essentially a 3-dimensional shape. So, vertices, you would have a 13 here, minus edges 15, right? Plus the number of faces is what we're calculating. What is the number of faces? Let's simplify. This is a -2 plus f is equal to a +2. If I solve this algebraically, I would drag 2 over to here via opposite operations. So you're going to add 2, cancel, add 2. The number of faces would have to be 4 faces, in theory. All right. Find the volume of a square-based pyramid using the formula 1/3. Capital B is the area of the base times the height. Now in this instance, the height dimension is the interior height here. That's 12. And this is a square base, you can tell, because the dimensions are the same here and here. So if the volume is equal to the area of the base times the height times 1/3, you could divide by 3 is more or less an amplitude. What is the shape of the base? Base happens to be a square. So if you calculate the area of a square, it's just the side dimension 8 squared, literally. So it's 8 times 8, right? And then times height would be times 12 over 3. You can, again, there's no sin in doing this with the calculator really. You could type 8 times 8 and times 12, figure out whatever the figure is, and then divide by 3. Or if you're trying to practice mental math skills, which is a good thing, all right, try to simplify it in its factored form, all right, by taking advantage of any relationships. There's a relationship between this 3 and this 12. So if I wanted to, as an alternative, I could simplify like this, all right? 3 divided by itself is 1, that's its common factor with 12, and 12 divided by 3 is left over 4. So that means that this is 64 times 4, or we could do 32 times 8, same product. All right, so 64 times 4 is 6, carry the 1 is 256. All right, if the units are consistently, and I should have checked that, centimeters, 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 this is centimeters cubed. 256 centimeters cubed. Now the last question below it, 22. Same triangle, but we're going to calculate the surface area. This is a little bit trickier because you have to sort of visualize it in real life. Right? I have drawn it to try to get it to work, but here's what I mean. If you were to sort of unfold this, right, the surface area it's going to be an area, so it's going to be centimeters squared is going to be your answer. Right, rather than centimeters cubed. We're not talking about the interior of this, all right? But we're going to have to employ a couple of different dimensions. We would need to know this dimension running this way, which is called the slant height, only for the reason that it is slanted. It's basically one of these faces. This would be the height, and this would be the base dimension if I were to look at it dead head on, not sort of from an angle here. All right, and we don't know what that is yet. Right? The area would be base times height divided by 2. This is the slant height. Right, because again, it's slanted in this orientation. How can I get that from the information that I have? Well, if I connect the edge here to the dead center of this square, all right, that can form a perfect right angle up to the vertex. Right? So the same view, well, the same triangle, but now looking into it, you know, would have this, I'll look at it from the side, would probably be more practical. I would have this basic right triangle here. This is H again. All right. The dimensions here, right, assuming that this is the center, would not be 8 centimeters, it would be what instead of 8? All right. What's half as far as the full extent of it? All right, 4, right? So in my simplified drawing, this is 4. All right. How tall is this still? 12. All right. And now I could figure out via Pythagorean Theorem this dimension, because it's really this dimension, and therefore it's really this dimension, to calculate the area of one of these faces. All right. It's sort of backtracking. All right. I know legs in this case. This is a leg, and this is a leg. How do I know that? Because they are perpendicular to each other. All right. And the missing dimension is a cross. Basically, I'm looking at this imaginary triangle here that I've sort of cross-hatched here, like so. Just because I want to know that slant dimension. All right. So, if the Pythagorean theorem is a squared plus b squared equals c squared, we could just change the dimensions if you want. The labels, I'll put that in like that. All right. We'll call this C H instead, right? Which is kind of jibes well because it's a hypotenuse anyway. Haha. All right, that's just dumb luck. All right. The height here, that is the original height, is either A or B. It doesn't really matter. It's 12. All right, and the B here is really a 4. All right. So this is 144 plus 16, which may give you a crummy number. Let's see, that's 10. Yeah, it's 160. Is equal to h squared. Right? This is an example of, you're gonna get stuck rounding. If h squared is 160, then as before, if you're gonna try to solve for not just h squared but regular h, all right, you would have to perform the opposite operation to cancel. So I'm gonna take the square root to cancel squaring and do the same thing to the opposite side. If it were possible to simplify this, try to, because this is not a perfect square dimension. Something like 100 would be a perfect square, 144 would be a perfect square, 196 would be a perfect square. This isn't one of those numbers that are famous. The best that you can do is maybe factor it to simplify. So what comes to mind is that this is 16 times 10, right? And the square root of 16 is 4. So you would end up getting stuck with this, 4 times square root of 10, if you factored it, all right? That really isn't the point of this exercise, right? How well you can simplify it, but it would work out that way if you wanted to. And that would preserve all of infinity, that is this decimal number, whatever the square root of 160 is. All right, anyhow, we have the height dimension now. All right. It is the square root of 160. Therefore, if I put this in the area formula, this would be 160. Right. What is the base, though, in this from this perspective, looking at the face of the pyramid dead on? It would be the 8 now. So you would have 8 times that. Right. We have basically all the information we need. I need to free up some space, so I'm going to erase a little bit. But before we actually do a calculation, let's sort of, again, rig the machine. Sort of set the controls before you turn it on, all right? the surface area, there's no formula that we have to work with, we could just reason it through, is the sum of several parts. If this is a pyramid with a square base, how many lateral faces are there? Right. There's a face, a face, a face, a face, and then technically there's another thing which is the base of the pyramid. Just to distinguish it, I'll use that word. But the faces that are the triangles, basically, that wrap around it and meet at this vertex, there's 4 of them, and they would be identical. So to simplify this calculation, we would say, all right, it's going to be 4 faces plus 1 base area. All right. The area of the individual triangles would be this, 8 for the base that runs this way, or that way if you like looking at it as such, times the slant height, which in theory would be this dimension up to the corner here, from the edge, not from the interior, which is 160 apparently, divided by 2. Right? But because there are 4 of them, I'm going to put this 4 on the outside. And even though I've encapsulated this in parentheses, it's just to show you what one autonomous face would be equivalent to. Because we're really just multiplying, we could maybe take advantage of the relationships here and here. Right? Before I do that, again, I'm setting the controls before I'm turning it on. The base is just the area of this square. That is the bottom of this. So this is just 8 times 8, all right, which is better known as 64. Okay, so now that we have the machine rigged up to calculate the surface area, the 4 faces plus the 1 base, it's a 5-sided polyhedron apparently, we could simplify just a wee bit. I don't recognize that phone number. Right. I'm sorry, I shouldn't be taking calls now. I'm not going to answer it either, so I don't know who that is. Yeah, I don't know who that is. It's probably a scam, whatever it is. Your 20-year warranty, right? Anyhow, if you want, you can simplify this factored incarnation of area. I didn't actually multiply it, I just simply wrote things next to each other. That's what they're worth. All right. This would simplify like so. All right. 2 divided by itself, common factor, is 1 down here, which means that the denominator is superfluous, you don't even have to have it, would change this to 4. Right. Which means what? It means that it's really 4 times 4 times the square root of 160. Right? To make it more concise before I enter it in my calculator, and I would because I have an irrational number here, this is really 16 times the square root of 160, right? Plus, what's 8 times 8? 64. Right. This I would type into my calculator, right? And maybe do it in the peculiar order of having 64 in front, all right? Only for the reason that I'd like to leave the square root of 160 dead last, just not to have a parentheses involved. It isn't wrong if you do write this first or enter this first, but make sure that you put a parentheses in here, all right? All right, so what are you gonna get? I'm gonna type this here, 64 plus 16 times the square root of 160. All right, if this is how I've entered it, that I've strategically put 64 in front, all right, then I could get away with not having to put another parentheses here. It really is important. If you want to be super careful, and I would never fault you for that, I really should be to set a good example, then put another parentheses in front of 16. All right, and that will make the calculator know you do that first. Anyhow, this should be fine. It shouldn't be able to have a problem with deciding between adding and multiplying. All right, enter, and there you have it. That is correct. All right, 266 and change. Round to the nearest hundred. So if this is 266.3 385, whatever it is, and we round to the hundredths place, that would be where the 8 is sitting, right? Based upon 5 being adjacent, this is approximately 266, there's a lot of flare on that too. All right, plus 39.39, what's the unit? Centimeters. It's a surface area, so it would end up having to be squared. Right? Areas, even if we're talking about a three-dimensional figure, surface areas are still an area, so your units would end up this way. Okay, 266.39. All right, and that is that. That is a summary, basically, of the material from Chapter 7 and Chapter 8, respectively. All right, let me put this aside. All right, the bundle of my lab assignments are due tonight. I know that there was some issues with there was a delay for one of the, maybe a couple of days ago. I'm going to look at it and see if it's functional still, all right? And then I'll talk to you, okay? Just spend this time, you don't have to submit anything, all right? Just spend this time, all right, finishing up your my lab, all right? That batch that is Chapter 7 and Chapter 8, okay? I've had a month so work on this, so please try to finish that tonight, okay? All right. Be careful out there.